Okay, here we go. Oops, just 1 second. I'm trying to. Okay. Welcome everybody to today's meeting of the online CUNY set theory seminar. We're very pleased to have New speaking with us again, and he will give us the second part of his lecture, and the title is Forcing with Overlapping Supercompact Extenders, and this is part 2. Okay, take it away, New.
All right, thank you, Atabta, and yeah, thank you for inviting me again. Okay, so the theme of this talk is going to be like some continuation of the last time. So last time I introduced the one of the critics forcings that appeared recently about dealing with the failure SCH when the singular kernel is already singular in that setting is in the core model. So or you can think of the ground model. So and then this is I think the motivation was from James, who asked me like, oh, is there something happening if I build up the supercompact version? So here it is. So the setup is gonna be similar as the last time. So assume the ground model does GCH, you have a sequence of kappa alpha. For alpha is less than eta. Where eta is small, so it's smaller than kappa 0. Eta is limit. Each kappa alpha is supercompact. The sequence is increasing, and the lambda is going to be greater than everything mentioned so far. And okay, the same goal is going to blow up the value of 2 to the sup of kappa alpha for alpha less than eta. But let's see what's going to happen here. In this setting, let me scroll out a bit. Okay, I think you can see more clearly. Okay. Oh, oops. Okay. So this time, I'm going to blow up the value of 2 to the sup to be at least the sup of J alpha of lambda, where alpha is less than eta, as stated in number 2. So it is higher. Maybe it's not super interesting, but the interesting part is now the cardinals in the gap between the sup of kappa alpha for alpha less than eta up to and including lambda, they are going to be collapsed. All the cardinals above are preserved. So it would be a bit more interesting if the value of J alpha of lambda is much higher than lambda. So that's why I put down as the first bullet in the result that, okay, you should, it's more interesting if at least J0 of lambda, you can set up to make it arbitrarily large. So in some sense, you're gonna get the failure of SCH at sup of kappa alpha for alpha less than eta. But you can also collapse some cardinals in between the singular cardinal and the lambda, where kappa alpha is something like lambda supercompact. And as in the silver style, the cardinal arithmetic behavior is going to reflect down at the sup of kappa beta for beta less than alpha. For every alpha less than eta limit, okay. So it looks peculiar and it looks a bit weird, but let me draw a picture in the next slide. So, okay, assume that eta is omega 1. Then in the extension, the cardinals in the which are not in the discontinuous gaps will be preserved. So what do I mean? So let me draw some line. Okay. So on the top, you're gonna have the supremum of kappa alpha for alpha less than omega 1. You have lambda above, and then you have J alpha lambda for alpha less than omega 1. And then the cardinal arithmetic says that 2 to the sup kappa alpha less than omega 1. is at, greater than equal to the sup of alpha less than omega 1 j alpha lambda. It's either equal or equal to the successor of the sup depending on the behavior of j alpha lambda and the conic lemma, like conic theorem about the kernel arithmetic. Okay, so for example, the first discontinuous gap that I'm going to consider is now going to be something like between the sup of kappa n, where n is less than omega, and then the next guy is going to be kappa omega. So I do not scale it correctly, but I just leave the gap so that I'll explain what's going on about the reflection. Kappa omega itself is a large kernel, so it's much larger than the sup of kappa n. And what's going on here is the cardinals which are not in the which are not in the continuous gap, so something like the bottom, like bottom of the line, they are going to be preserved. Cardinals on the top of kappa omega is going to be preserved for a while, until I think it's going to be sup of kappa omega plus n, and then there's going to be some gap between that and kappa plus, sub omega plus omega that we are going to consider. Above the sup of kappa alpha for alpha less than omega 1, the cardinals between the sup and lambda, including lambda, are going to be collapsed. So the cardinals that I had labeled in green, let me see. Okay. These cardinals in this interval are going to be collapsed, including lambda. The rest above lambda, everything is preserved. And you get the failure of SCH. But not only that, you're gonna get some reflection going on. So what do I mean? I mean that, for example, in between sup of kappa n and kappa omega, you're gonna have some reflection going on, which means that from you have like lambda, so there's gonna be some reflection of lambda, which I will call lambda omega, and there are more. So you're gonna have some reflection of Jn of lambda, for example. So now it's gonna be reflection of it's gonna be Jn omega of lambda omega. So it's gonna be some ordinal between greater than lambda omega and kappa omega. And what do we mean it reflects down is the cardinals in this interval, for example, that I also highlight in green, they are going to be collapsed, and the rest of them between sup of kappa n and kappa omega, they are going to be preserved, and you're gonna get the failure of SCH, which means 2 to the sup of kappa n less than omega is going to be at least something like sup n less than omega, j n omega lambda omega. So it's something that is similar in the in silver style. And yeah, it happens at every continuous gap. So the same thing will happen between the sup of kappa omega plus n for n less than omega and kappa plus omega and plus omega, and so on. So this is how reflections happen. Okay, and I think the most interesting bit that I think Moti pointed out is that, well, if it is possible that for kappa, which is the singular kernel in the ground model, it is possible that you can preserve kappa, collapse kappa plus, and then preserve kernels above kappa, kappa plus, by fixing some particular value of lambda. So in this case, lambda is going to be kappa plus, where kappa is a sup of kappa alpha, where alpha less than omega 1. So, okay, let's take a look for a bit. So in this case, what's going on? I preserve the supremum of kappa alpha for alpha less than omega 1. And the things in green will be collapsed. So it's going to be from the sup of kappa alpha together take a plus up to and including lambda. So lambda in this case is just the sup and then plus. So the only kernel which is collapsed is just kappa plus. And then above lambda, which is kappa plus, everything will be preserved. Okay, so this is how kernel arithmetics goes on in this setting. Okay, let me erase a bit. Oh yeah, before that, any question about the kernel behavior? Okay, good. So let me erase everything. It's a lot. Okay, now I'm starting to talk about the technical part, which will lead to the forcing construction. So if you remember last time, the story about the Gittix forcing using a sequence of strong kernels. So I'm gonna in this talk, that oftentimes the slide will have like 2 columns, and I'll try to compare between 2 situations. Okay. So for this slide, for last time on the left-hand side, you consider the context of strong kernels. So suppose J from V to M witnessing kappa being lambda strong. So what does it mean? It means that in the target model, M is closed under kappa sequences. M can compute kernels correctly up to including lambda. Then in order to capture strongness, you have to derive the extender of length lambda. And then I have a notion of domain and MC going on. So the domain is just the subset of lambda of size kappa. You have MC, which is just a function represented by the map J alpha to alpha for alpha in D. And I define the measure 1 set A to be large if MC is in J of A. And then you can say that we concentrate on the collection of mu's, which I will call objects, which are functions where the domain is a subset of D, the range is a subset of kappa. And I also define the coherent part, which is the partial function from lambda to kappa, where the domain of F is actually the domain that I defined before. So in particular, it has size kappa. So that's the story from the last talk. Now I'm going to imitate the same story, but in the context of supercompact kernel. So now in the context of supercompact kernel, you have the target model, which is closed under lambda sequences. The extender that you have to capture to preserve supercompactness in this setting, I wanted to have length J of lambda. It's possible to get somewhat shorter length, but I think it's more convenient to get to derive the extender with this length in order to capture the supercompactness. So once you derive the extender and then you take the derived map from the extender, you're gonna recover the supercompactness of kappa. Now I try to imitate the same game. So the domain D is going to be a subset of J lambda, and I want it to be interesting. So it's gonna have size lambda. MC is the same as before. MC is going to concentrate on mu. And the domain of mu is going to be a subset of D. The range at this time, the range is going to be a subset of lambda. So the range is much higher. The coherent part is going to be a function, partial function from J lambda to lambda, where the size of domain is lambda. I mean, the domain is going to be just the domain that I defined in the last previous three bullets. So yeah, I just said roughly how the story goes. I'll go into a bit more detail later on. And now, once I want to compare between two large cardinals. So I have kappa 0, kappa 1. They are large cardinals. I have extenders E0 and E1. And let's say A is a measure 1 set in E0 of D. So A is going to contain objects, which are just some sort of functions. And in the story of the strongness, is quite simpler than the supercompactness in the following sense. A concentrates on the objects, mu. The coherent has size kappa 0. So I'm considering the coherent with respect to kappa 0. So the size of F is going to be kappa 0. And if I want to compute JE1 of F, it's simple because kappa 0 is below kappa 1, which is the critical point of JE1. So if you compute JE1 of F, it's just going to be the pointwise image, of JE1 of F. And if you compute the what's going on about coherent, so the story last time when I defined forcing and the one-step extension, you have some sort of composition of mu inverse. And then when I look at M1, which is the out VE1, the coherent will be represented as JE1 of F composed with MC1 inverse. It's going to be F with some, there's a little bit of work. And also the size of the measure 1 set with respect to kappa 0 is going to have size kappa 0. So if you compute JE1 of A, it's going to be just the pointwise image. And then the story about composition with MC1 inverse is going to be, you're going to recover A. And the story of this slide basically says that there is a collection measure 1 set of mu such that if you compose F with mu inverse, you're going to get something that you want. And if you compose A with mu inverse, you're going to get something that you also want in the forcing. Now, it's a little bit more problematic in the setting where kappa 0 and kappa 1 are supercompact. So first of all, A will concentrate on the object's mu as usual. But now the first problem occurs. Because now the coherent has size lambda, you cannot say anymore of what JE1 of F is exactly, because the size of F is lambda, which is greater than kappa 1. So when you take JE1 of F, you may not end up getting, well, you will not end up getting the pointwise image of F. And then once problem occurs, it's like a domino. So the other things will be problematic as well. So The story of supercompact kernel seems to be good for a while, in the sense that you can derive the extender, you can define the domain, you can define the measure one set as usual. But then once you jump into the story of forcing, then something different has to happen. Okay. So now we have to fix these issues. And yeah, let me start with some assumptions first, so that it's more convenient to analyze what's going on. So I have the sequence of supercompact kernels, kappa alpha for alpha less than omega 1. Lambda is greater than the sup, such that the first one is for each alpha, that is the extender E alpha on kappa alpha, comma, J alpha lambda, witnessing some lambda supercompactness. And if you derive this, and then there's a little bit of work saying, checking that from the map J alpha, witnessing kappa alpha being lambda, once you derive E alpha, you're gonna get that J alpha of lambda is equal to J E alpha of lambda. And then you're gonna save a lot of info, a lot of details about what you need. And you also need some definability. So for the extender E alpha, I need J E alpha of S alpha computed at kappa alpha is going to be lambda. And there are much more going, there's much more going on right now. So for beta less than alpha, I want to also address the value J E alpha of lambda inside the out V E alpha. So what do I mean? I want some function T beta alpha from kappa alpha to kappa alpha, such that J E alpha of T beta alpha computed at kappa alpha is going to be J E beta of lambda. So I want to save a lot of details about what's going on before alpha inside the out VE alpha. And also I want to save some information about E alpha. So there's a function H beta alpha from kappa alpha to V kappa alpha, such that J E alpha of H beta alpha computed at kappa alpha is going to be E beta. And in particular, from number 3, what you're gonna get is that J E beta of lambda is less than J E alpha of kappa alpha. Any question about this setting? I know it's a lot of details going on right now. Okay, so good. So just keep in mind that at each alpha, E alpha will save information about what's going on before stage alpha. Okay. Okay. Now, before I jump into the forcing, I want to analyze what is the useful measure one set that I want to save in order to define the forcing. So let me start off with just one extender. So suppose I have only one extender E. I have J from V to M, witnessing kappa being lambda supercompact. So I drop all the subscripts, derive a kappa, comma, J lambda extender E. And then JE is going to witness kappa being lambda supercompact. And JE lambda is going to be J lambda. And we're gonna repeat the story as in the last time. Okay. Okay. Yeah. So for now we can just consider just one extender. Later on, I will analyze what's going on with two extenders and say a little bit about arbitrarily many extenders, because that one is a bit complicated. Okay, so D is a domain. If D is a subset of J lambda, it has size lambda, and I want D to save some information. So I want lambda plus 1 to be a subset of D. So a few cardinals which are important that you have to keep in mind is kappa and lambda will be in D. So those are two important cardinals. I define MC as usual. So it's going to be just the map JE restricted down, restricted to D inverse. So roughly, what it looks like is it's going to map JE of alpha to alpha for every alpha in D. And I think it's useful to write something down a little bit. So a few cardinals which are useful. So from the first bullet, you know that kappa and lambda, they are both in D. So in particular, JE of kappa and JE of lambda is going to be JE pointwise image of D. And if you compute MC JE of kappa, you're going to get back kappa. MC of JE lambda, you're going to get lambda. So these are two important values. And I define A to be large with respect to E of D, even only if MC is in JE of A. Okay. So now, again, I'm going to split the slide into two columns. The left-hand side, what I'm going to say about the left-hand side is what is going on about the behavior of MC inside the out VE. So the outer power of V by E. And on the right-hand side, I'm going to say about what A concentrates on, okay? So for the left-hand side, the domain of MC is going to be the pointwise image of D with JE, which is a subset of JE of D. And the range of MC is just D itself, just because how MC works. And D is a subset of J lambda, I mean, it's equal to JE of lambda. And the second bullet, the size of domain of MC is lambda, which is smaller than JE of kappa, just because kappa is lambda supercompact. And MC is order preserving. So on the right-hand side, the large set or E of D will concentrate on what I call objects, which are the collection of mu, such that the domain of mu is a subset of D, the range is a subset of lambda. And this is just by the reflection, right? On the left-hand side, you can see the domain and the range of MC are the subsets of J of D and JE of lambda, respectively. So that's a collection of, that's a measure one set of mu such that domain of mu is a subset of D, the range of mu is a subset of lambda. The size of domain of mu is less than kappa. The thing in between basically said, just to remind you that you have the function S that represents lambda. Oh, sorry. Okay. So because I dropped down the subscript, so I will write it down again. So one of the assumptions I have for E is that I have a function S from kappa to kappa such that Js of kappa is lambda. So that is a collection of, there's a measurement set of mu such that the size of domain of mu is exactly S mu of kappa. And you can also say mu is order preserving. And I think that that's all the last bullet. Since kappa is less than lambda is less than J of kappa, so that's a measurement set of mu such that mu of kappa is less than S of mu of kappa is less than kappa. So these are some details about what you can concentrate on about mu. I think the most important bit that I think that you have to keep in mind for now is the first two. The domain is a subset of D. The range is a subset of lambda, and the size of domain of mu is small, so it has size less than kappa. Okay. Okay. And of course, if you later on, like if you want to, for example, derive a scale in this forcing, there's more things that you have to say. So if you want to say more things, you can say so, as long as it concentrates on, is something that is something where MC behaves inside the out of VE. So for example, if the domain D has more information, for example, I fix gamma and I say that, okay, JE of gamma is in D. I can say that there's a measurement set of mu such that the domain of mu contains JE of gamma, and mu of JE of gamma is gamma. It's going to be something that I'll recall again once I say something about the collapsing cardinals. And of course, it's usual story for every large set, a measure one set. I can assume that A is a subset of OB of D. And again, it's the story of the extender. So for each D and D prime, if D is a subset of D prime, there's a projection going on. So there's a, sorry, it's not projection. I mean the elementary embedding, ID D prime from out V E of D to out V E of D prime. Okay, let me recall a little bit that element of out V is out VED is of the form F sub ED, where F is going to be a function from OB of D to V. So this is a particular element inside out VED. And from, since D is a subset of D prime, you have the natural projection map pi D prime D, mapping mu to mu restricted down to D. And this will induce the elementary embedding ID D prime. And yeah, as usual, you can project down to a normal measure. So if I can define A to be in E kappa, if kappa is in J E of A, and E kappa is just a normal measure. And then since there's some projections going on, you can say more thing about how E of kappa interacts with, for example, E of D, where D is a fixed domain, for example. And yeah, the particular correspondence is for each gamma in A, for A in E kappa. So A concentrates on ordinals. For each gamma in A, you can kind of correspond to some mu kappa for some mu in for some object mu. I say it very vaguely, but yeah, just to give some picture. And yeah, some useful example which I will not emphasize so much. I mean later on, but for at this point, I'll say a little bit. Just because lambda is JE of S kappa and is less than JE of kappa, so I can say something like this will reflect down to a measure one set of gamma less than kappa, such that S gamma is regular because lambda is regular inside the out VE. And in the language of objects, you can say that it can reflect down to a measure one set of mu, such that S mu of kappa is regular. So you can see some corresponding between gamma and mu of kappa here. Okay, let me. Okay. Any questions so far? Okay, cool.
Can I ask a question real quick? I mean, not that I really, I'm following anything,
Okay.
but except when you're talking about MC, it was like some kind of an inverse function. So I was expecting the like range to be, I don't know.
Did I say
think it was
wrong?
back yeah, the range and domain of, just trying to.
Okay, so let me think. So what's going on about the, let me write down. Yeah, sorry, I'm a bit too fast. So if I consider JE raised to D itself, it's going to map gamma in D to JE gamma, right? This is how JE raised to D works. And MC is just the inverse. So it's going to be JE of gamma to gamma for gamma in D. Okay. And okay, I mean, D can vary. So it's hard to say what mu concentrates on exactly in terms of D. But what you can say roughly is, well, MC is the domain of MC. So you can see that it's a collection of JE of gamma for gamma in D. So this is going to be just JE pointwise image of D, which is the subset of JE of D, of course. So one thing you can say that if you concentrate on mu, where the domain of mu is a subset of D, and also the range of MC is just D. This one you cannot say much about how range of mu looks like with respect to D, but one thing you can say is D is a subset of J lambda. So you can say that the range of mu has to be a subset of lambda. So the picture that you have in mind is something like this. So this is D, and then this is lambda, and this is D. The possible height is much higher, so it's J of lambda. And then mu is something like this. Okay. So it's something from the domain which has very high domain to something lower.
So JE of lambda, what? Sorry.
Yeah, J of lambda.
JE of lambda
yeah.
is D or something?
Sorry, J of lambda is
D.
no. JE lambda is just the possible like the height. So I just draw it roughly, because in general, it's always a case that D itself will not be J of lambda, but it's just going to be some subset of J of lambda of size lambda. So the height, when I say the height, well, it's roughly, but I said that the domain is going to be subset. The domain of mu inside the measure one set is going to be subset of D. And yeah, you can later on you can extend D more and more. So in the forcing, D will be closer and closer to J lambda itself. But in terms of the condition in the forcing, D is going to be just the subset of J lambda, which of small size. So smaller than the size of J lambda. I have to say a little bit about I think in the preparation you can say something that the size of J lambda is going to be much higher than lambda. So you can think of it that way. Not only the height of J lambda is higher than lambda, but the cardinal of J of lambda in V is going to be much higher than lambda in general, because J is not the map from the supercompact measure, is from the extender. So the value of J of lambda is not necessarily have size lambda plus or something like that. Yeah, there's a big gap between the lambda and J of lambda over right here. And J lambda is the same as J E of lambda.
Oh, that's more helpful. Okay, I kind of understand.
Okay, cool.
Thank you.
Yeah, sure. Okay. Let me erase. Right. Okay, now we are going to discuss a story about two extenders, which is going to be a little bit painful. So here you go. So now I have two extenders. First, I have two cardinals, kappa 0 and kappa 1. E0 is kappa 0, comma, JE0 of lambda extender. E1 is kappa 1, JE1 of lambda extender. And I recall some important details about what E1 has. So first of all, I have the function S1 from kappa 1 to kappa 1, representing lambda. I have T01 from kappa 1 to kappa 1, representing JE0 of lambda. And I also have H01 from kappa 1 to V kappa 1, representing E0. And now when I say MC1, I mean MC with respect to kappa 1. So I have, just to be get familiarized, I have D1, which is in JE1 of lambda of size lambda, and MC1 is just JE1 residue inverse. So the first bullet is, we know that JE1 of T01 of kappa 1 is JE0 of lambda, which is the length of E0, right? Because E0 has length, E0 extender on kappa 0, comma, JE0 of lambda. And E0 is JE1 of H01 of kappa 1. And there are a few cardinals that I want to compare. So kappa 0 is less than kappa 1, where kappa 1 is the critical point. Kappa 1 is less than lambda. Lambda is below J0 of lambda, and it's below JE1 of kappa 1. And one more thing, I think I rather to skipping this bullet. I think it's a bit too complicated. But I basically I want JE0 of lambda to represent something correctly, in some sense. Okay. So from the first bullet, that JE1 T0 1 kappa 1 represents the length of E0, you reflect down to a measure one set of mu, such that H0 1 of mu kappa 1 is going to be an extender. It's going to be an extender witnessing kappa 0 being something like I think S1 mu kappa 1 supercompact, and it's going to have length T01 mu of kappa 1. And I also compare a few cardinals. So from the left-hand side, you translate to the measure one set on the right-hand side. So kappa 0 is going to be below mu of kappa 1, is below lambda. So lambda is JE1 of S1 of computed at kappa 1. So kappa 1 less than lambda translates to mu of kappa 1, less than S1 mu of kappa 1, less than T01 mu of kappa 1, and less than kappa 1. So the most important bit here is once you reflect down on the measure one set, all the important cardinals will be below kappa 1. This is the most important thing. So the reflected of lambda, the reflected of JE0 of lambda will be below kappa 1. The reflection of H01 mu of kappa 1 is going to be an extender inside V of kappa 1. And yeah, the last bullet, I will not say much. Okay, yeah, so two things is you have to reflect the extender correctly in terms of length and how much supercompactness you get. And the second one is once you reflect down, everything will be below kappa 1. Okay. So yeah, in conclusion, oh boy. Okay. Let me check the time. Okay. Oh, not conclusion yet. Now I want to analyze a little bit more about the coherent functions, which is going to appear in the forcing construction. So just recall that you have two cardinals, kappa 0, kappa 1. They are large cardinals. Now I have the function f, which represents a coherent part inside the domain. So f is going to be a partial function from JE0 of lambda to lambda. So it's something that kind of homogeneous with the objects with respect to kappa 0, because just let me say a little bit, inside E0 of D0 is going to concentrate on the collection of mu such that the domain of mu is a subset of JE0 of lambda and the range is a subset of lambda. So f and mu with respect to kappa 0, they are kind of like homogeneous in some sense. But anyway, f is a coherent function. The domain of f is going to be a domain with respect to kappa 0, which I'll call 0 domain. D1 is a 1 domain, and D0 is a subset of D1. And the first proposition that I'll say is there is a measure one set of mu in E1, D1, such that once you perform a conjugation, it's going to be a coherent function that lives inside some reflection of the coherent poset, the original coherent poset. So what do I mean? What I mean is, okay. Let me scroll. Okay, like this. I mean that, so remember that lambda will correspond to S1 just because lambda is J E1 S1 kappa 1, and J E0 of lambda corresponds to T01 of mu kappa 1 just because J E0 of lambda is J E1 T01 of kappa 1. So once you pick the object mu in E1 D1, the reflection of the coherent function that we should expect is something like S1 mu kappa 1 and T01 mu kappa 1. And the point is, and the point is, once I look at what's going on about the out VE1. So what does it look like about mu compose F compose mu inverse in out VE1? So you map F by JE1, right? So you're gonna be the thing in the middle is going to be just JE1 of F, and mu, when you take a map JE1, the representation of mu is going to be MC1. So I want to prove that once I define the big F as MC1 compose JE1 of F compose MC1 inverse, you're gonna get something that is still in the script A lambda JE0 of lambda. So what I'm going to claim here is, if I can prove that this big F is equal to small f, then the proposition is done. And why is it true? So let's set the big F to be this conjugation. First, I want to check the domain. So F gamma is in domain of F, even only if gamma is in domain of MC1 inverse, which is a range of MC1, and the range of MC1 is D1. So I get the first mark that, okay, gamma has to be in a domain of big F, even if the first one, gamma is in D1. Second one, once you compute MC1 inverse, I think it's better to write down. Okay. Gamma is in domain of F, even if the first one, gamma has to be in the domain of the rightmost guy, MC1 inverse, which is just the range of MC1, but the range of MC1 is just D1. Once it passes through the first step, then I want MC1 inverse of gamma to be in the domain of JE1 of F. So I want MC1 inverse of gamma, which is JE1 of gamma. Just because of the definition of MC1, I need it to be in the domain of JE1 of F. But this is true if and only if gamma is in domain of small f. And the third one, so when it passes through the second stage, what is the value of JE1 of F computed at JE1 of gamma? So I want JE1 of F computed at JE1 of gamma, which is now JE1 of F gamma. I need this to be in the domain of MC1 inverse. But domain of MC1 inverse is just the pointwise image of D1. And remember that I require D1 to contain all ordinals up to and including lambda. But okay, this is it, if and only if F gamma is in D1. Remember that F is just the F is just the partial function from J0 lambda to lambda. So in particular, for number 3, okay, the range is a subset of lambda. So J of lambda, J of gamma, sorry, F of gamma is in lambda, but I require D1 to contain all ordinals up to including lambda. So this one you get for free. Number 1, I need it to be D1. The second one, I need it to be in domain of F, but the domain of F is just D0 as I define, as I said at the beginning, and D0 is a subset of D1. So we are in a good shape that the domain of big F has to be exactly the domain of small f. So this is what it buys us. So the first one that you get is domain of big F is a domain of small f. Furthermore, by the calculation that we did, you're gonna see that the big F of gamma, so from the big F of gamma, if I compute with MC1 inverse, it's gonna be JE1 of gamma. And then I map it by JE1 of F, the small f. So this is JE1 of F gamma. And once I map it to MC1 inverse, it's going to be just F gamma. So you actually get back what you need. That, okay, if I compute big F of gamma, you end up getting the small f of gamma. So in conclusion, the big F is equal to the small f, and the small f is just the coherent function from, it's a coherent function from JE0 of lambda to lambda. So that in conclusion, there's a measurement set of mu such that if you perform a conjugation, you're gonna live inside the correct reflection. So if you remember what's going on about last week, you just have to compose with mu inverse to make sure that things will be reflected down to the correct part, the correct reflection. This time, what you have to do is you're gonna have to perform a conjugation in order to get back what you need. Okay. All right, since I kind of almost ran out of time, so let me speed up a bit. Okay, I haven't erased everything. Okay. So okay, now I did the coherent part. Now I'm any questions? Sorry. Okay. Now I'm going to consider the measure one set part. So fix kappa 0, kappa 1 as usual. D0 is a subset of D1, they are domains. A0 is of measure 1 with respect to E0 of D0. And for each mu, which is just the object, so it's just a function from in E1, D1, I define A0 sub mu as the collection of tau in A0, such that the domain union the range is a subset of domain of mu. So this story is going to be similar to something like the relation about the Mackey dot increasing in the story about like supercompactness. So that story is like you have x0 below x1 if x0 is a subset of x1, and other type of x0 is below something like x1 intersect with kappa. So it's increasing in that sense. This one is going to do some similar story. Okay. So I define A0 sub mu as the subset of A0 in some sense. And that's a proposition saying that that is a measurement set of mu, such that if you perform a conjugation where the item in the middle is A0 sub mu, it has to be of measure one set in the correct measure. So what do I mean? I mean that originally E0 is represented by JE1 of H0, 1, kappa 1. So once I use an object mu, I need the reflection to be going down to H0, 1 of mu kappa 1. And the last term in the proposition is just the reflected domain, because the H0, 1 mu kappa 1 is an extender. So I can say about the domain as well, right? And the domain in this sense is going to be the pointwise image of D0 with mu. This one I'm not going to prove. It's a little bit lengthy and complicated. So skip this part. I'll remind you more when what's going on when I define the forcing. Okay. Okay. So here's a recap. I have two supercompact cardinals. I have E0, E1. They are extenders on kappa 0, JE0 lambda, JE1, kappa 1, JE1 of lambda. And I have some previous some information about what lambda, JE0 lambda, E0 represent inside E1. I have domains D0 subset of D1. F0 is just the coherent with respect to kappa 0. A0 is the measure one set with respect to E0, D0. Then there is a measure one set of mu such that first one, everything, every important detail about E0, once you reflect down, those things will be below kappa 1. Second one is something that I skipped before. Second one, if I perform a conjugation with F0, which is the coherent part, it's going to leave inside some correct reflection in the coherent process. And yeah, the last one is if I perform conjugation with A0 sub mu, then it's going to live inside the correct measure one set. Oh. And yeah, the E01, yeah, it's a typo. So E01 has to be some extender where the length is kappa 0, comma, j sub small E01, lambda 1, witnessing kappa 0 being lambda 1 supercompact. So I state it in the way that it looks reminiscent to the original way of saying kappa 0 is lambda strong. Okay, more things can be said when I consider arbitrary extenders. Basically, you have to make sure that everything commutes. So it makes sure that the forcing actually works as what you want. Okay, now I'm going to define the forcing. And as usual, the story about the prickly type forcing, I will start off by simplifying the definition by saying what a pure condition is. Remember that the sequence of large cardinals has length omega 1. A pure condition is going to have length omega 1. Each coordinate P alpha is going to be an order pair F alpha, A alpha, such that F alpha is the partial function. So just recall you that it's a partial function from J E alpha of lambda to lambda, such that the domain of F alpha is actually a domain. So it's just one of the Ds that we described earlier. A alpha is in E alpha, D alpha. So it's just a collection of mu's, the collection of objects. The sequence of domains is subset increasing. And I define a direct extension in the usual way. So P is a direct extension of Q if for every component, Fp alpha is stronger than Fq alpha. And AP alpha should have fewer options comparing to AQ alpha. So what do I mean? I mean that once you restrict the object in AP alpha with DQ alpha, that object with respect to DQ alpha has to be inside AQ alpha. This does make sense because just recall that the alpha P is a superset of the alpha Q. So for each mu in this size, it will correspond to something like D restrict down to Q, DQ alpha. And it has to be in the measure one set with respect to Q. Okay. So how much time do we have? Okay, 15 minutes. Okay. Now I'm going to say about what the one-step extension is. Suppose P is PL as before. So I list down as the first line. So I list down just the first 5 components. So P0, P1, P2, P3, P4. Mu is in A2. So mu is an object, it's just a function. The one-step extension of P by mu is going to be a condition Q, where at F2, I'm going to override F2 by mu. So what is F2 O plus mu? It's going to be a function where domain is just the domain of F2. if gamma is in, if gamma is in domain of mu, then the F2 or plus mu of gamma is just mu of gamma. Otherwise, it's going to be F2 of gamma. So I write it down in brown. The part about Q0 and Q1, I'm going to squish them down by performing conjugations. So F0, F1, G0, G1. I'm going to compose them with mu and mu inverse. I think I should write it down. Sorry. And I need domain of tau. Yeah, forget about this part. So the important part is once you perform a conjugation, this thing will, I want to say the last bit first. So for the last bit, Q3 and Q4 is different from the story from the last week. So I have to make sure that the objects inside B alpha, inside from A alpha to B alpha, I want to make sure that the object is large enough so that it will save important information that you use for the proof of the Prickett property and deriving the failure of SEH and some the collapsing kernels. So I want B alpha to be the collection of tau so that tau is larger than mu in the sense that I write down below. So I want domain of mu and union range of mu is a subset of domain of tau. And the important story is once you take a look at the blue part, the Q0 and Q1, the B0 and B1, for example, they will be of measure 1 with respect to the small ei2, which is going to be some extender witnessing lambda 2 supercompactness. And remember that everything lambda 2, J sub small e sub I2 lambda 2, everything here, they are all below kappa 2. So in conclusion, the order pair Q0 and Q1, it will live inside some much smaller forcing. And when I say that it's much smaller forcing, it lives inside something like V sub kappa 2. And yeah, for B3 and B4, just make sure that when you perform one step extension further, it does make sense. And yeah, if you take a look at Q alpha for alpha greater than or equal to 2, you can consider it as the condition inside P sub E alpha for alpha greater than or equal to 2. Originally, the condition P is living inside something like P sub sequence E alpha for alpha less than omega 1. Okay, so yeah, this is the most important feature of this kind of forcing. Once you perform a one-step extension, you actually squeeze things down below, and it's much more like smaller below. I define P to be stronger than Q if P is a direct extension of n-step extension of Q. So you first off extend Q by using n many objects, and then you enlarge the domains, you shrink down the measure 1 sets. It has a lambda double plus chain condition. it has a pretty property, some factorizations, and this will show that, remember I said at the very beginning that most of the cardinals, well, the cardinals which are not in the discontinuous gaps, they will be preserved. So you need some tricky property to say this thing. And it also has the strong tricky property, which also makes sure that lambda plus is preserved. So it's a similar story as in the Gittix forcing. So I think that, and yeah, it also adds a scale. Yeah, actually, I don't have time. So the way of deriving a scale is quite complicated. But the point is, the derived scale will give you the failure of SCH. Okay. So now the part that is different is the cardinals between the sup and lambda, including lambda, will be collapsed. So let's say that gamma is in the interval, and I want to make sure that it will be collapsed. I think this one will have cofinality omega 1 in the extension. So let's say cofinality of gamma is large. So what is a candidate? The candidate has to be like, so what's the candidate here? The candidate of making sure that cofinality of gamma in VT is going to be omega 1 is, remember that if P is pure, each condition will be something like F alpha, A alpha, alpha less than omega 1. And the usual candidate is going to be mu alpha computed at the JE alpha pointwise image. So yeah, there's some story about, well, there's a part where supercompactness comes in, because it's a usual fact, right? If gamma has large cofinality, then the sup of pointwise image of JE alpha of gamma is going to be below JE alpha of gamma itself. And this will tell you that this kind of sequence will be a cofinal sequence with in gamma of order type omega 1. And yeah, this is how it works. So you make sure that each D alpha, which is the alpha domain of P, you have enough information. You have the sup of JE alpha pointwise image of gamma, and JE alpha of gamma is in D alpha. Every mu has domain containing these two guys. Make sure that mu of JE alpha of gamma is gamma. Then you use some standard forcing argument to show that the sequence that I just wrote down is actually a cofinal sequence in gamma. And that will give you a fact that the cofinality of gamma in VT is going to be omega 1. And this will imply that all the cardinals between the target singular cardinal up to and including lambda, which is the cardinal where kappa alpha is like lambda supercompact. Everything in between this interval will be collapsed. And yeah, I think that's probably okay. Yeah, for the final comments, I think later on, so I define everything here with the supercompact extenders. So maybe some people are not familiar with supercompact extenders because it doesn't, we don't use them that much, or at least we haven't seen them that much. And the question is it possible to define using like supercompact measures? And the reason, the answer is yes. You can define this kind of forcing using some supercompact measures, but you have to combine it with some strong extenders as well in order to get the desired failure SCH. The part about the supercompact measures will make sure that the cardinals will be collapsed. So it's something similar to supercompact diagonal peripheral forcing, something like that. And the part about supercompact extenders will be responsible in a similar way as the Gittix forcing that I described last week. And yeah, I think that's all I have. All right, thank you so much. I know it's very technical. Yep, thank you.
Thank you.
Thanks, Neil.
Great. Are there any more questions or comments? Okay, it seems like everybody is satisfied.
Okay.
Yeah, it was very technical, but very interesting. So
yeah,
thanks for that.
Yeah,
it must have been hard work preparing that.
No, it's just that well, the research is about building a forcing. So if I don't say what the forcing construction is like, then I'm gonna say, okay, here's my theorem. That's all.
Indeed, yes. Yeah. Well, thanks for all your work on that. That was great.
Sure.
Okay, I guess that was it for today. Everybody have a nice weekend, and I'll see you next week.
Have a good weekend, everyone.
Okay.
All right.
All right.
Bye.
Bye-bye.
Thank you, everyone. Have a nice weekend.